And then I guess just send it to the.
Here's sirens everywhere. And
Was that the part of the science was when it finished and you were just
Waiting for the.
yeah.
no, it's not clear. Why you know?
I just saw the screen. I thought it was
No. It's just something that was open on my screen. It's not even your linear algebra. The linear too. No, we cut the calculus. Okay, so last time on calculus, we were covering in the shelters, and now we're covering the real life from derivatives. Yeah. Okay, sorry. So we're back in calculus. We're ישורת אחרונה with the final stretch. Thank you. We're reviewing and maybe proving some of the function analysis theorems. And I'll remind you which one we've seen yet. So we've mentioned the mean value theorem, which says that if a function is continuous and its y value is below the x-axis and then above the x-axis, then what must happen in between? Yeah, there is an intersection, a point. I'll show it to you. Yes, if f of a is below 0 and f of b is above 0, so between a and b, there is a point whose y value is exactly 0, given that the function is continuous. Otherwise, it could jump over the axis. So that's the mean value theorem. The second theorem was Weierstrass, which says that if the function is continuous between a and b, including a and b, square brackets, including a and b, then it will get a maximum value and a minimum value. Fermat says that if you have a local extrema, points in an area, two-sided area on the x-axis, where the value at the center point is the highest or the lowest, then if the function is differentiable, the derivative must equal 0. That's the way we find points who are suspect as extrema. And then we saw an example with x squared minus x to the fourth. We said the function is continuous everywhere and differentiable everywhere. So between 0 and 1, there must be, by Weierstrass, a maximum and a minimum value. Where can they be obtained? So either when the derivative is 0 or at the edges. Why at the edges? Because there it might be a maximum, but not a local maximum, because the function was going up and then continue to go up. So it wouldn't be a local maximum, but it would be the maximum in the area. It's not what happened here, but it might have been. And then we find all the suspect points, and at 0 and 1 over square root of 2, the derivative is 0. 1 is the other edge. So the suspect points are 0, 1 over square root of 2, and 1. We plug them all into the function, and indeed we found that 0 and 1 are the minimum points, and 1 over square root of 2 is the maximum point. And we answered the analysis question, what are the maximum and minimum values, sorry, of these functions. Next, we learned about Rolle's theorem, which says, and this one I want to start with GeoGebra already, because that's the last one, and the next one is Lagrange and so forth. And so just let me see what is the number of the lecture.
Harry Potter as the things.
What?
Lagrange.
Lagrange. Okay, lecture 21. Lecture 21. So we'll start with the row, and I'll use GeoGebra to show you. Let's take the very function from the last example. So f of x is x squared. F of x is x squared minus x to the 4. And I'll put 2 points in, 0, 0, and 1, 0. And I'll take the line between A and B. That's the chord. A line between 2 points on the graph is called a chord. Okay. So I have some graph here. I chose 2 points. And what are the assumptions of Rolle's theorem? That f of A equals f of B. So I took 2 points with the same y value. Can you think of in discrete mathematics, can you think of functions that do not have 2 such points?
I don't remember the name.
Xad-xad-key, 1 to 1, right? So if the function is 1 to 1, then Rolle is completely useless. Do you agree? But it makes sense. Why? Because Rolle states that the derivative must be 0. Think of a 1-to-1 function, the linear function, a straight line, right? 2x plus 3. What is the derivative of 2x plus 3? 2. It's never 0. Okay? On the other hand, x cubed is also 1 to 1, yet its derivative does equal 0 at some point. So it's not if and only, but in any case, I took a graph where f of A equals f of B. And the Rolle theorem states that the derivative must equal 0 at some point, not the edges. At some points, not including the edges. Here we know that the derivative is 0 here as well. You see, by the way, it's a local minimum, right? But I don't care about that. Rolle says that between A and B, not including A and B, there must be another point where the derivative is 0. Which is that point here?
The local maximum.
The maximum here, right? Write it. And y equals quarter, right? And the point is 1 over square root of 2. We found that out last time, and a quarter. Okay, so at this point, and the derivative is 0. So I'll start by writing this up, and then it will give me a good segue into the next theorem. Example, let's look at Rolle's theorem applied to f of x equals x squared minus x to the 4th at 0, 1. So it looks like this, and indeed, f of 0 equals f of 1, and for c equals 1 over the square root of 2, it so happens that f prime of c equals 0. I'll tell you in a short while why I wanted for you to see the graph of this function. Any questions so far? So now, let's look at the following example. I'm changing up the function a bit, plus x. And I change the p point to be 1, 1. So what did I do? I like to say that I rotated the function, but I'm aligned. It's not actually a rotation, it's more of a twist. I don't know how to say. I don't think there is a name for it. But at least for the sake of I don't know, philosophy discussion, think of rotating the function, right? I didn't rotate the function. The point being here is that beforehand A and B were both at the same y value, right? After the change, this is 0, this is 1. The B point is much higher, right? So Rolle's theorem does not take effect. Okay, the derivative doesn't have to be 0 somewhere in between. It actually does, because there is a local maxima here, but we don't care about it at all. It doesn't always have to be. Can anyone guess geometrically what the next theorem would state? Think about the rotation. That was the original theorem. We have these 2 points and that chord, and we have this point here. What did I draw here? What is the blue line? No, the blue line as itself, the line itself. What does it represent? This point is the maximum, right? But as a function, y equals a quarter. What is a function? It has to do with the graph. No. The line and the point, what is the connection between them? What would you say? No. Anyone else cares to guess? I'll give you a hint. Okay, okay. What will happen if I zoom in here? It's the tangent line, exactly, right? The blue is the tangent line to the graph. Agreed? What's the connection between the tangent and the chord?
They're parallel.
They're parallel, right? So what would I expect there to be here? Let's say.
It's a secant.
No.
Yeah, what's the question again?
I'm going over it. At Rolle, I'm restating Rolle in a geometrical way of thinking. I took the chord between 2 points, right? And I found out this is the tangent here, right? So here I take this chord. What do I expect there to be? Exactly, at some point, the tangent will be parallel to this chord. That's exactly Lagrange theorem. I will state it by words first, and then I will state it mathematically accurately. But that's what Lagrange says. And why is it so important? That will be the next thing that I'll say. But in this case, Rolle is a specific case of Lagrange. So why do we study rho first? Because in order to prove Lagrange, we need rho. So that's the way to do it. But what I'm saying, and I'll show you, choose a random point for start A. A equals half. No. A. Oh, sorry. Second. A. Second slider between 0 and 1. 0, 1 in increments of 1/10. Okay. And now I'll write the tangent line. Y equals f of A plus f prime of A times x minus A. That's the formula for the tangent line. And now I'm going to move the point. See, that's the tangent line. Do you agree that the red line is the tangent line to the graph? Is there some point at which it is parallel to the chord between A and B? So that's kind of right. It's probably not exactly right. Agree? That's what second A f of A, let's put the point as well. So this is what Lagrange is saying. There is a point at which the tangent line is parallel to the chord. I'll write it up and
For every function.
yes, Lagrange has no differentiable and continuous, right? But other than that, that's the function. It's always happening. If you look at it geometrically, it makes sense, right? Because if the function started going up, it must come down again to get back to the other point in a sense, right? So it always has to be something like that. That's not a proof, but yes, it always works. It's
Proved by everything that goes up must come down.
yeah, exactly, yes. If it's continuous, that's the mean value theorem, to be honest. But exactly that. All the theorems that I'm running through, that we usually run through, maybe in normal classes, I would probably have another week or another 2 weeks. But the way Calculus 1 is built is that most of the time we talk about the limits and the foundation. And then after we have the idea of limits, we can have continuity, and then we can understand that much faster. But most of what I'm saying here is being taught in high school. Specifically Lagrange, no. Lagrange is a new thing. The other theorems, I think every high school student would guess, right? If I went from below the x-axis to above, then I had an intersection. I have a maximum and I have a minimum. At the local extrema, the derivative is 0. All these theorems we use a lot. Lagrange we don't use a lot directly, but we do use it implicitly. And Lagrange is the reason that when the derivative is always positive, if I started the sentence, I will finish it. If the derivative is always positive, that means that all the tangent lines are going up, increasing. Lagrange says the chords are parallel to the tangent lines. So if all the tangent lines has a positive slope, then all the chords have positive slopes, meaning that the function increasing. Okay, Lagrange is the way we prove that if the derivative is positive, then the function is increasing. Okay, I will say if you didn't get it, it's okay. I will say it again in a short while. And I'm just excited to say it already. And so Lagrange states that given a good function, I will be accurate shortening. And every chord, meaning the line between two points on the graph, is parallel to some tangent line. Every chord is parallel to a tangent line. By the way, it's not bidirectional. There could be a tangent line which is not parallel to any chord. And I'll give it for you as homework. Find a function and a tangent line to the function that is not parallel to any chord. Lagrange said every chord is parallel to a tangent, but there could be a tangent that is not parallel to any chord. Think about it. It's not like super important, but it's a nice problem to mull at. Okay, mull at. And okay, so far. So now I'll actually state the theorem. Lagrange theorem. Given a function f which is continuous at AB and differentiable at AB, not necessarily including the edges. That's the assumption. That's it. In Rolle theorem, it was close. Look at Rolle for a second. I assumed f is continuous at AB, including A and B, and differentiable at AB, not necessarily including A and B. And what was the next assumption? That f of A equals f of B, right? Lagrange does not have this added assumption. I just need continuity and differentiability. Then, so try and help me to state the theorem. I wrote in words what it says. It's important for you to state it, because then it's not another formula you have to memorize, but if you understand it, it makes sense. So I have the chord between A and B, and what does the theorem state?
The derivative is
At some point, then there exists a point C between A and B such that who measures the slope of the tangent line,
the derivative.
right? Such that the derivative at C is parallel. What does it mean that it's parallel? This is the slope of the tangent line, and what does it equal to?
B minus A over H.
The tangent, this is the slope of the chord, right? Slope of the chord, not cut of the tangent. This is the slope of the tangent. We wish it to be equal to the slope of the chord, right? Slope of the chord.
Oh, it's equal to f of B minus f of A over B minus A.
Exactly. See, when you understand what should be written there, the formula becomes clear. That's what Lagrange theorem states. This is the slope of the tangent line. It must equal the slope of the chord. There is some point which the tangent line actually equals the slope of the chord. And I'll give you a second to digest it. And then I'll go back to the example above and find the actual red line. Because this is, I don't think that is true. It looks kind of parallel, but if we go, hey, Sammy, if we zoom out, we see that the lines aren't actually parallel. See here, it's not the correct point. We'll calculate the accurate points in a now.
What I think about this theorem? Because even 2 points, you know that it has to increase or decrease from one point to the other, right? The important thing is that at some point it's equal to the slope.
Like I said, the important thing is if the derivative is always positive, then all the tangent lines are a positive slope, and therefore all the chords are positive slopes. That, by definition, means that the function is increasing. And I think that's what you're missing, and I'll do it in a second. I'll define what's an increasing function, and I'll show you that it's equivalent to saying all the chords are increasing. And that allows us to connect between the local derivatives, the differentiability at the local points, and the entire story. It means the function is always increasing.
Yeah, I mean, I don't understand. It isn't necessarily always increasing, but it's overall increasing.
It's always increasing.
It's always
Yes.
Which is what is it? Experiment.
If the derivative is always positive, then the function is always increasing between every 2 points. That exactly says equivalent that the chord is having a positive slope.
Yeah.
So that's exactly what Lagrange gives us. Yes, sir.
Can I ask about the second derivative? I thought that was the second derivative.
No, the second derivative, first of all, every derivative says the same thing. So if the second derivative is positive, then the first derivative is increasing. Right?
Yeah.
That's like accelerating your car, right? So that means that the function is smiling, right? Because the slope keeps going up. But what I'm saying could be also linear. The derivative is always positive. I have a constant velocity, positive velocity. So I keep increasing, but not the speed keep increasing, right? So the derivative, if f prime is positive, the function is increasing. But I'll do it.
Is it enough to say the derivative or not the second?
Yeah, no, but second derivative is not even necessary because you could have a smiling function going down, right? If I'm stopping, yeah, if my velocity is negative,
Yeah.
no.
No, you're right.
Yeah.
If it starts like that and then it goes like that.
Yeah, the speed is increasing because in absolute value it's decreasing. That's what
The second derivative is increasing, but the derivative isn't always.
second, not increasing, you're confusing
Sorry, it's
positive and
positive.
increasing, yes.
It's
The
positive.
second derivative is positive, so the derivative is increasing. But it might be negative, so increasing is going up to 0. Yeah. And then it looks like this. Right, this function has a positive second derivative and a negative first derivative, and the function itself is decreasing. That's like slamming the brakes in the car. Okay. Okay. So, example. And let's get back to f of x. It's not back there, not back there. And consider f of x equals x squared minus x fourths, and I added an x and at 0, 1. F of 0 is 0, f of 1 is 1. So that's the point here. A is 0, 0, B is 1, 1. What's the slope of the purple chord? The slope of the chord between 0, 0 and 1, 1. What is it?
1.
1 minus 0 over 1 minus 0, which is 1. So Lagrange promises me that the tangent at some point must equal 1 as well. Let's find this value. So there exists a point C between 0 and 1 such that f prime of C equals 1. The tangent is exactly parallel to the chord. Now let's calculate it. Oh, I think it's a third degree polynomial. I'll use Wolfram to actually calculate it. Okay, so f prime of C is 2 times C minus 4 times C cubed plus 1. Oh, yes, equals 1, so it won't be that horrible. We wish it to be equal 1. That means that 2C minus 4C cubed equals 0. Lucky us. And C times 2C minus times 1 minus 2C cubed equals 0. So C equals either 0 or minus
Take out C probably.
third root n. And
No, you didn't take out.
oh, right. I didn't understand what you said. You're right. 1 shouldn't be surprising, to be honest. It's the same, and it's not minus. Sorry. And 1 over square root. Yeah, it should be obvious from the way I built this function, but whatever. Sorry. So it's 1 over the square root of 2. And drum rolls. Thank you. A equals 1 over the square root of 2. Okay, you see, it was a minor fix then. There, it was very close to what we found by hand, but now it's actually parallel. And now,
Isn't it surprising that before it was
the same value? It's
yeah.
not surprising. It's because the way I built the function. I just added x to the function, so it's the same point. It's not surprising at all. It's surprising that I didn't think about it. But it should have been obvious. It's actually the way you prove the theorem as well. But the other way around. You remove x from the function and then you make it into roll. So yeah. Okay. And so that's what we have. And now all the theoretical talk we had about increase the connection with the increasing function and the sign of the derivative, I will write down. Yes.
So can I just ask this theorem? It needs to be that both the function everywhere is differentiable.
Differentiable in continue, but differentiable implies continuity. The only difference between the two is the edges. You must be continuous at the edges, but you don't have to be differentiable at the edges. Like the square root of x, which is continuous until 0, but it's not differentiable at 0. So it's a small thing, to be honest. The main thing you need is differentiability. Okay, so we're almost done, by the way, with the theorems. We only have Cauchy left, which is an abstractization of Lagrange and L'Hopital rule. L'Hopital rule is rather technical. Lagrange is like the last main function analysis theorem. So yeah, that's for the future. In any case, definition. We say that f is increasing or monotonic increasing or monotonic increasing at the set A if, and now just a short discussion. In sequences, do you remember what's the definition of an increasing sequence is? Yeah, what's the definition of monotonic increasing in a sequence? Every point is every element of the sequence is larger than its previous, right? In functions, you cannot do that because there is no previous. Saying 0.1. Does it has a previous point on the x value? No. So we need to define continuity and monotonicity differently. You cannot say between every point and its previous. You must say between every point and all its previous points. We could do the same with the sequences, but it's just a waste of time. You can't say that the sequence is increasing if A of n plus k is larger than A of n for every k. It is true, but it's a waste of time. In function, you must do it this way. So if for every 2x values x1 smaller than x2 from A, it is true that the value of f at x1 is smaller or equal to that at x2.
We can even say it under set A.
And
You have a set.
where is it increasing? That's like the segment if you prefer, right?
And
It's
X.
yeah, exactly.
You go x0.
We want to say like it's an area.
It's like an area, yes. Yeah. So in Hebrew we say תחום עלייה, domain of increasing. Yeah.
You put x0 is not x2.
Thank you.
Aliyah is increasing.
What?
Aliyah is increasing.
To go up.
It's not like less, so it's like an increase. That's together.
I didn't understand what you
Yes.
It's
said.
asking the meaning of Aliyah in Hebrew.
Aliyah. Yes.
Yes.
I didn't get the Hebrew word. Yeah, Aliyah is increasing and politically saying that coming to Israel is increasing and leaving Israel is decreasing. Yeah, exactly that's what it said in Hebrew. Aliyah is going to step up. Yeah. Like also if you're becoming religious, you're coming back with an answer. And if you're becoming secular, you're going out with a question. חוזרים בתשובה או יוצאים you're going out with a question.
I learned this last.
There is a lot of politics in the naming of things.
What's crazy in Hebrew?
חוזרים בתשובה.
That's
coming back with an answer.
when you're religious, you can go from not religious, it's your Shera.
Yeah, you're going out with the question. Yeah. So again, coming to Israel is Aliyah, is increasing, and living in Israel is decreasing. Yordim haaretz, you're decreasing. Okay, yes. I didn't. It's not my, I'm not stating any values, just Hebrew mathematical points of parallelity. Okay. So a function is increasing if when you go up in the x values, the y values go up as well, or equal, like we did in sequences, and decreasing, obviously, that's the f of the second point is always smaller than the first one. I won't even bother writing. Okay, great. So conclusion, if f is continuous at AB, and differentiable at AB, and f prime is positive at AB. So I have a function which is continuous and differentiable, and the derivative is always non-negative. What can you say about the function? Then f is increasing at a. So that conclusion is something you know from high school, right? But now we see how do we prove that. We don't actually see, we will prove the conclusion. I didn't prove the theorems coming up to it, but I will prove the conclusion in a bit. And it's just implied from Lagrange's theorem. Yes, I mean, it seems like you want to say something.
No, I was realizing that I was confused how our conclusion is different to our definition. But the conclusion is just using our definition in logical statement.
No. So it's a good question because it's important. The derivative is not that. The derivative is the limit of chords. That's the difference between the two. I wish to take some chord between, look at the GeoGebra, okay? Saying that the function increased between A and B. Think about a car. I think it's helpful. If you start driving in Ayalon, and after 10 minutes you're measuring your point and your location, sorry, then you're forward in Ayalon, right? You started in Shalom, and now you're in the Halakha.
No, but it's not alone, you're just stuck on the same spot.
You're the second, it's the definition of inclusion. Small or equal. As long as you're not driving in reverse, you're moving forward.
Well, that actually,
Okay, yes. Okay. Hi. So you started at Ayalon and you ended up at Halakha, right? That's some time has passed. You cannot ask about your speed. Suppose you just started driving and there was a jam, so your speed was 0 first. And when you got to Halakha, you stopped and the speed was 0 as well. But still, you must agree that you moved forward, right? So like that said, then at some point in time, your speed must have been positive, right? You couldn't get from Ayalon to Halakha only driving backwards, right? So, The theorem says that if your speed was positive through the whole ride, then you must have moved forward. So it's not the same thing because the derivative is the speed, the velocity at every distinct point. And the theorem said that if at every distinct point your slope was positive, then altogether you move forward. By the way, this does not describe this graph because here the slopes are positive and then they're negative a bit. So it's not really matching this graph. It's when you sped up and then you slow down, like I said. But the derivative is at local points, right? At each point, I find the limits of the chords around this point. But you're looking at the chord between A and B, two far away points. That does not mean does not mean derivative. And also you see the tangent line is somewhere in the middle, right? The point in time where what would you call that? If that is speed, what would you call it? If I went to Ayalon to Ashalom at 2 o'clock and at 10 past 2 I was in Halacha. What does it tell us about the speed I drove at? Does it necessarily mean that my speed was fixed, was constant? No. But what measurement could there be?
Time,
Acceleration.
No.
average speed.
Average speed, that's what I was going for. Average speed. So at some point I drove exactly at the average speed. That's what Lagrange tells us. Okay? The average speed is the slope here, and at some point I was exactly about on the average speed. And in general, what I wanted to say, again, here are increase and decrease. But it could also be the story for only an increasing function. Okay, so let me prove that theorem and its conclusion. Proof. And take x1, which is smaller than x2, both of which are from A, B, by Lagrange, there exists a point C between x1 and x2 such that the tangent at C is equal to the chord between x1, fx1, and x2, fx2. That's what Lagrange says. I took two random points. I took the 2 points on the graph above them. The line between them has the slope of the tangent. Slope of the tangent in C is equal to the slope, not the same line, it's the slope of the chord between, meaning that f prime of C is equal to f of x2 minus f of x1 over x2 minus x1. Now, what do we know about the derivatives? What is the assumptions here? The assumption here about all the derivatives. All the derivatives are non-decreasing. No. All the derivatives are positive, sorry. And since f prime of c is larger or equal to 0 by our assumption, then the chord has a slope which is increasing. What can you deduce from the fact that the slope, I keep saying increasing myself, I'm mistaken obviously, positive, not increasing. And what can you deduce from the fact this is larger or equal to 0? What can you say about the denominator x2 minus x1?
Positive.
It's positive, right? So what can you deduce about the numerator?
But it's given.
It's also positive. Since x2 minus x1 is positive, then f of x2 minus f of x1 is non-negative. Agreed? And QED. That's what we need. If you don't see why it's what we needed, therefore, I'll write another step. F of x2 is larger or equal to f of x1. Now we finished.
So that I'm not confused, basically what we're saying is if for all x from A to B, fx is increasing.
Negative. That's the
When?
result. No, that's the result. The delta, the assumption on it is that the derivative is larger or equal to 0. That's what you know.
For all x. The
Yes.
derivative is-
Yeah, the derivative is always positive. And you deduce that the function is increasing.
Yes.
As you do in high school, it's not, I think part of what's confusing here, it's not new. You knew it already.
I finished high school 6 years ago, I don't remember what you're talking about.
No, I think if the derivative is positive, that the function is increasing.
Yeah,
That's all I'm saying, really.
yeah, and it doesn't apply to the function we were saying.
No. The example here, it doesn't apply because the function is decreasing here. Yeah, it's not a good application for this. But it's also a new thing. I didn't use it as an example, right? That's after the example I said increasing. Let me give you an example. Look at f of x equal x cubed. What's the derivative? 3x squared, which is also always, bigger or equal to 0, right? That is why x cubed is always increasing. Even though it's 0 at some point, right?
Yeah.
We are all look at x cubed. Always increasing. Because every 2 points, every couple of points, you will take the chord between, it equals to some tangent, some derivative, and the derivative is always non-negative. So it always must be in an increasing direction. That's what Lagrange gave us. Yes.
Is this categorization for whole functions or for ranges too?
For what?
Because
The assumption is differentiable and continuous. If it's not differentiable, then you don't have a derivative, and then it doesn't matter.
No, not the question. You showed us a function that is always positive. My question is, can we say that a sector or a range is positive? Like
Yeah.
I'm talking about
That's why I said in the set A, which Sammy asked about.
okay.
Like x squared is positive between 0 and infinity. I'll write it as an example, right? Another example, f of x equals x squared, and f prime of x is 2x. At 0 to infinity, it is true that f prime is larger or equal 0, therefore s is increasing. And I'll just show you the parabola. And it's increasing from 0 to infinity, right? You have a domain of the increasing, right? A domain of decreasing. So yeah, it doesn't have to be always. In x cubed, it's always, right? But in x squared, it's between 0 and infinity. Agreed? Now we can finally solve an analysis question which I like. Example, find how many roots does the following equation have? X equals cosine of x. Roots of an equation are points which are solutions. I'm asking you how many solutions does the equation x equals cosine of x have? Do you have any guess before we start to study it?
One.
One is an option, 2 is another option. Sammy? That is not an answer. That's like Star Wars. What do you mean?
Stronger line is wrong.
Oh, but it's not, but it was vertical, it's not good. It's not vertical, it's not supposed to be
X
vertical.
is vertical.
But it's y equals x, it's not vertical.
No, wait, this is x equals cosine of x?
Yes.
Okay, so, I mean, it depends.
So x equals cosine of x is all the points on the cosine of the. Okay, well,
I think,
one.
wait, three, bro.
Okay.
We'll go with.
So I have 1, 2, 1, 3.
Yes.
That's 1, 3, 1, 2. Okay, yes. And any other answers? Infinitely many. Thank you. It's the wrong answer. Thank you. Yeah.
You wanted the other answer, you didn't say it.
Yeah, I wanted the wrong answer. I don't like when you know the answer.
You
It's
said,
not fun.
you said fast, not accurate.
Yeah, no. Yes, but it was fast, yeah. I'm good at, you know the joke, I'm good at fast math. Yes, okay. And, okay. And so I won't give you the answer yet, I wish to give you, if you feed a man a fish, you will be full for today, but if you teach him how to fish, he will be.
You want to like, immediately.
I don't remember how to say it in English. Okay, he will kill many fish along his line. And so I wish to show you how we can answer that question ourselves and not using guesswork. So, solution. Do you remember the one of the mantras, the slogans, which I told you is very important?
No.
Perfect.
Put everything to the left.
Yeah, you know, x minus cosine of x equals 0, and build the function h of x equals x minus cosine of x. Our question is equivalent to how many roots does h of x have? Agreed?
Yeah.
That's like the most important step. And afterwards it's easy. You see why. What's the derivative of h prime of x?
1 cosine.
1 plus sine of x. If it was high school, then students, innocent students are in high school are being taught to find how many zeros that the derivative has. How many times the derivative is equal to zero? Infinity. So that is not helpful at all. That's the non-innocent thing is understanding the question we are actually interested in. We're not interested in how many times the derivative is zero. We are interested in whether the derivative is positive or negative. Can you know that easily?
It's both.
It's both.
I mean,
Is it? When?
I know it's zero either, right?
Yes, it's never negative. Why? Because the minimum value of sine of x is -1. Okay, so by the way, the slope of x here is super important. If the question was 2x, 3x, or x over 10, the answers will vary. Okay, but for specifically x, because the slope is 1, you get that the derivative is always non-increasing. What does it mean about age? Non-negative. And what does it mean about age?
Yeah.
Therefore, age is increasing. And therefore has at most how many roots? One root. You see how the calculus help us? We're not doing guesswork anymore. The calculus tools gave us a really huge step, and it says it's either 0 roots or 1 root. These are the only 2 options here. Yes, Sammy.
Is that to say then that a cubic graph is not increasing?
Why no? It is increasing, and we saw it in a second.
Because it goes up and down and up.
It
Right?
doesn't have to. X squared, x cubed is only going up.
Okay.
Zero.
Because the derivative is a parabola, which might be above the axis and always positive. Or
If the derivative is a parabola, would that be increasing?
if it's the parabola, the derivative is always a parabola. If it's above the x-axis, then it's only increasing, and if it's below, then it's increasing, then decreasing, then increasing.
So it isn't completely increasing.
Yes, doesn't have to be. Just x cubed plus x.
If a function is only increasing, then it only has 1 or 0 essence. Sorry, 1 or 0.
Okay, that's a function whose parabola. Let's derive the function. The derivative is 3x squared plus 2x, which is positive until this point. That's the derivative. In gray, you see the derivative. So until this point, the original function, the purple one, is increasing. Once the derivative is negative, the original function is decreasing, right? And the second that the derivative is positive again, the original function is increasing.
Okay. But
Yeah,
for an increasing function, a function that is completely increasing,
yes.
you can only never have 1 or 0.
No, you can have many roots, just so infinity. Because when you have roots, you don't have to go below the x-axis. You can kiss the x-axis. You say, people, go to the x-axis, you touch it, and then you go back up.
Okay.
I'll show
No,
you.
but that isn't a completely increasing function.
It is. It is. It is. That's exactly x cubed. Look at x cubed. Now I understand the question. Look at x cubed. Is x cubed a completely increasing function?
Not decreasing.
No, completely increasing.
Yeah.
Every point is strictly larger than the previous point.
No.
X, it is true.
Yes, sorry.
X cubed is 1 to 1. It never return to the same point twice. Yet the derivative is 0.2. What so? That's what you asked. You asked if there, if, okay, that was your
You
question.
know what my question is, I'm asking my question.
No,
Let's go back to the.
yes,
Go on. You said that the function is true that. Wait,
where,
wait,
no,
We
it's
have
not
a
that.
check with semantics.
No, I pasted it in the wrong place, yeah.
You said h of x is increasing. Therefore, it has a boost on this, that's what you said.
Yes, the function itself, okay, yes.
So does that go for every function that's increasing?
Oh, I see, but it has nothing to do with the derivative. Are you asking about the derivative or the function?
What's that function?
Oh, I see. No, yes, yes, because if you're strictly increasing, you want one. Therefore, you cannot get the y value equals 0 twice, because you want one. Okay, I thought you were asking about the derivative. Derivative could be, have many roots as well.
It's okay.
Okay,
Wait, and strictly increasing is when there's no y.
yeah, exactly. It's not constant, and if it was a constant, the derivative would be completely 0 within this segment, which you would notice.
Also, in terms of the notation, like the arrow would have a line.
I don't, what do you mean notation?
One plus sign it. One plus sign it. Okay, then.
No, that can equal 0. That can equal 0. That's important. And I'll show you the group. I don't want to show you the graph yet because we didn't finish answering the question. I'm chopping that up to another example. Okay. So we know there at most one root. How can we know whether there was a root or not in general?
Check that one by whether it's below.
Yes, but more abstract than that. We found out that age always increase. Let's check its values at the edges of the increasing domain. It could be that it's increasing between 0 and 1, and then I'll check the edges between 0 and 1. But here it's increasing between minus infinity and infinity, and we want to check the y values at minus infinity and infinity. Could we plug in minus infinity and infinity? No. So what do we do when we cannot plug in the number? We calculate the limits. The limit as x goes to minus infinity of x minus cosine of x. What does that equal to? What's the limit of x? Minus infinity. And what can you say about cosine of x? It's bounded. So it's negative infinity plus bounded, plus or minus bounded, whatever. Minus bounded, it's the same. It's negative infinity. And that's why, Sammy, you have a point below the x-axis. See what I mean? Joe, you don't need to randomly plug in points. The limits does the calculation for you. And the limit as x goes to infinity of x minus cosine of x similarly is infinity. So there exist points below and above the x-axis, and since h is continuous as a combination of elementary functions by the mean value theorem and H cross the x-axis and finally we have exactly one root because we've proved that there is at least one root. The h function must cross the x-axis, and we proved that it's increasing, therefore 1 to 1 it has at most one root. Altogether we have exactly one root. And now we can use GeoGebra and show you the way it looks. We are all. So the function x, that one, the function cosine of x, is that one algebraically? We cannot solve this question. We cannot find the exact, not within our tools anyway. I'm not sure if within mathematics there is a known way to do it. But we see here there is one point. The function we are actually doing analysis of is the difference f minus g. That's h. That's the red function. And what can you say about the red function, the difference function? It's always increasing. It's always increasing. Therefore, it has at most one root. And when does this root appear? Exactly when the two different functions meet each other. So that's a graph of the question we just saw. We didn't need the graph and we didn't use the graph at all, right? But we did study it without using it. Like when we calculate the limits of h, we calculated the limits of the red line. And there are infinity on the right and negative infinity on the left. Therefore, it must have crossed the x-axis once. Using the derivative, we found out that the red line is monotonically increasing. Just for a visualization, if I switch x by x over 10, how many solutions do we have between the two functions? Many, right? And if you look at the derivative is negative, then hey, that's not the derivative, sorry. And the difference is positive, negative, no, increasing, decreasing, increasing, decreasing. And if we look at the derivative of hx, it's too many functions. Okay. So the derivative of h of x is positive, then negative, positive, then negative. Therefore, h of x is going up, going down, going up, going down, and then infinite many times. That makes the question that much harder to solve. And luckily, that's the reason, not luckily, it's because of my choice. I didn't ask you how many solutions does x over 10 equals cosine of x has. Because it's much more complicated. That's when it's actually x. Then using calculus, it was quite easy. So, any questions so far? Lastly, in the theorem section of the course, Cauchy theorem. Cauchy theorem
always comes back to pandas.
Yeah. It's also abstract Lagrange. It's not that generalized, sorry, generalized Lagrange. Generalized Lagrange, not abstract, generalized. And it says as follows. Assume F and G are continuous at A, B. And differentiable at A, B. Also assume that G prime is never zero at the open segment AB. Then there exists a point C between A and B such that the ratio between F prime of C and G prime of C, the ratio between two tangent lines, the slopes of two tangent lines, is exactly the ratio between the chords. Any questions at all? In a second, I will show you why this is such an important example, because it seems like such an obscure question. The ratio between the tangents is the ratio between the chords. Why do we care about it? And you'll see in 2 seconds why is that such an important theorem. Yours have something to say?
No.
Just if you don't care about it? No. Good. Okay. So look at the specific example, an important one. Consider the specific case where f of A equals g of A equals 0. Then by Cauchy, what do we get? We get the ratio between the derivatives. What does it equal? But f of A equals g of A equals 0. The ratio of the functions themselves. The ratio of the derivatives equals the ratio of the functions. Who can help me? Say what is this rule? When do we replace the ratio of the functions by the ratio of the derivatives? Thomas, this is another question. I need your help. In which theorem do we replace the ratio of two functions by the ratio of the derivatives? L'Hopital rule.
I was about to say this looks very similar to the theorem.
That is exactly L'Hopital. Well, exactly is a bit much, but that's a certain it's a certain case of L'Hopital rule.
Actually, very, very important.
It's not purposely, you saw the way it's built. It's the left another function analysis theorem. Okay.
You said is the last thing we drew.
Yeah.
How many weeks ago I brought it up?
Yeah, but consider the limit as x goes to 0 of 1 minus cosine of x over x squared. Okay? So the numerator goes to 0. The denominator goes to 0. That's the same as saying the actual value of the function at the start of the segment is 0. Therefore, the ratio of the function is the same as the ratio of the derivatives. It was not true if it wasn't 0 over 0. It is true in infinity over infinity. It's a rather complicated proof, but if it was 1 and 2, it wouldn't work because you have these values here that are not deleted. But when they are 0, it's the easiest case to see, they are deleted and the ratio of the derivative is equal to the ratio of the functions, which means we can replace the functions, each of them by their own derivative. The derivative of 1 minus cosine of x is sine of x. The derivative of x squared is 2x. See, that's the ratio of functions. And that's the ratio of their derivative. And what is that limit?
0 over 0.
But you have sine of x over x. It's a lot of work to get the limit of sine of x over x. What's the limit of sine of x over x? 1. So what is the limit here altogether? Half. You can do L'Hopital again, but it's silly. Because for L'Hopital, you need to know the limit of sine of x over x. But in exam, if you do L'Hopital here, I won't mark you down at all. It is true.
If you do L'Hopital here, what would you get?
You get cosine of x over 2. Cosine of 0 is 1, so you'll get half. Because the L'Hopital rule is true, it's a true statement, right? You won't get a mistake. And it's just circular logic, that's why it's silly, but it is correct. So yeah, so next Tuesday we will do only L'Hopital. It will be a much more technical session. We will calculate limits using L'Hopital, and we'll fix a date for a session before the exam to go over the questions you might have. And that's it for today. See you on Tuesday.
I have a question that's not connected to the next lesson. The